Okay, are you ready for the next presentation? So, hi everybody, I'm Tsybulkin. I'm an entrepreneur, an engineer, and sometimes a researcher. And today I'm going to talk about machine learning, and more specifically about how to create a self-learning robot using Python and reinforcement learning. So let's look at animals. Most of newborn mammals can't walk properly. And from the very first hours of their lives, they start to learning how to do this. So nobody teaches them. So they do this by themselves. A newborn baby, a human baby, waves her hands, legs, like in a few months she can turns around and starts learning crawling. Then she practices like walking, running, jumping, and so on. Imagine a robot that also can't walk properly in the beginning, but it can learn how to do this, and maybe he can't learn how to do more complex movements. So my presentation is about how to build the software agent, which actually in the beginning can't know nothing about their goals, can't achieve actually these goals, but later it learns how to do this. So what is reinforcement learning? Wikipedia says that this is an area of machine learning. This was inspired by learning how animals actually learn. This is a software agent that interacts with an environment and tries to maximize some notion of cumulative function, cumulative reward. So let's see examples actually. Let me rephrase this. First of all, we have no supervisor in reinforcement learning. The second important thing that our agent uses trial and error approach. So it interacts with the environment and learn what is best, what is good, what is bad, and this is how it learns actually. It should have some kind of sensors, should have the ability to sense, and it should have goals. So this is our first example. This is a small robot developed in Zurich Technical University, ETH. So it has reaction wheels. It has a few sensors, so it can measure its angles and some other parameters. And it uses these reaction wheels to get some angular momentum, and then after braking this wheel, it jumps on its edge and then uses the same wheels to keep balance. So it looks like as you trying to keep balance, so you use your hands, and it uses these reaction wheels. So it's amazing, isn't it? So when I've seen this first time, I was like impressed very much. And I decided to build a self-learning robot who actually could learn this kind of motion using reinforcement learning. So first, let's look like engineers created this robot. So actually, they use standard optimal control theory. So they design a model, then they describe the motion, the dynamic of this object in terms of differential equations, then introduce control, and the last thing you need to check or analyze this, the whole system with your control on stability and robustness, and maybe tune adjust this control. So it's not that complex, so it's quite simple. And we won't do this, so we will build a software agent that can learn by himself how to do this. Before we do this, let me describe how reinforcement learning looks at high level. So we have the environment. So we do nothing. We actually know nothing about environment, about physics, about laws, and so on. So our agent actually can do some actions, and he can measure its state. And so environment says that your object comes from one state to another state. So you got these sensors, and you can measure this. And last thing, you have this reward signal. Reward signal is something that reflects your goals, actually. So if you do well, so you got some reinforcement, you got some positive rewards. So let's once again, we don't need to know anything about our environment. So let's build these four elements of reinforcement learning system. So first element is state. So it's our position or our coordinates or other parameters we measure. Second element is actions. Actions may depend on the state. So at some state you can do these actions, on another state you can do another actions. The third thing is policy. So policy is how we choose the best action at some particular state. And rewards. So state. Very important thing about state. So what you need to remember. the less amount of states you have, the faster your agent will learn. So if you include to your state anything, or I would say everything you can measure, so you got like million or maybe billions or maybe more states, so it's not good. In our case, what should we add to our state? Any thoughts? Maybe position, but what kind of position? Angle. Yeah, good. What else?
Not angle, but angles.
Angles. Which angles?
I mean, if we are in the solar space, it's a real world, look at two angles.
No, we have just planar. Let's consider like simple model. So we have just plane, and we have cube is our like a square. So we have just one angle. Actually, we need to know the angular velocity. So because assume that your cube, for example, angle is close to 0, but you have like a dynamic system, and angle is changing rapidly. Say it increases. It's one state, and you have to do. You have to take some action in this state, and if your angle like changing in opposite direction, so you have to like take another action. So we need to know actually the derivative of our angle or angular velocity of the cube. So we have this alpha and angular velocity of the cube, and I include omega, which is actually the speed, angular speed or angular velocity of our reaction wheel. Why? Who knows? Who can guess?
Because the speed of reaction is restricted by some kind of ability to react fast of this wheel is many physical measurements.
Look, our model does not depend on omega, so it depends only on its derivative actually, and we control this, so we can increase our reaction wheel speed or decrease it. For example, we can break it. Okay, sorry?
L, what is that?
L is this distance.
And then what is that?
R is the radius of our reaction wheel. Okay, so actually it's easy. So first of all, we can use only two parameters in our state without any omega. But I'd like to create like a more real model. So assume that you increase the angular speed of your reaction wheel. Increase, and it could go to infinity, so it's not good. And that's why actually when our angular velocity of our reaction wheel exceeds some limit, so we can't actually increase it anymore. You see, we can only decrease it. And the same for the other direction. Rewards. rewards. So we have actually two kinds of rewards. One reward is immediate reward. So when you go to from one state to another state, and you take some action. If you come closer to your goal, you may assign some, say, positive reward for that. So your agent could be reinforced. But in many cases, you can't say that you are closer to your goal. So assume you are playing chess and or some other examples. For example, in chess. So you play, say, e2, e4. So what does it mean? Is it good or bad? You don't know. So and that's why we have this delayed reward. So the reward which your agent got when it goes to terminal state. So if you win your party, you got, say, big reward, plus 100. And if you lose, you got big penalty. In our case, when our angle of our cube is close to 0, we assign reward, say, 10. It doesn't matter, actually. And otherwise, we assign some small penalty, -1. The final element is our policy. How we choose our actions. And here we have a few common policies. First common policy is greedy policy. So when you choose the best known action, I mean the action that leads to the best known state with the highest estimate, current estimate. So let's look at the example. For example, you know that you are in state 1, and you know that if you take one action, you go to state 2, and if you take, say, the second action, you go to state 3, and you know that, and you have also other actions, but you don't know so the estimates of other states is 0 because you don't know, you never been in this kind of states. So you choose the action that leads to the best, to the state with highest current estimate. So this is greedy policy, and as you may see, this kind of policy leads to suboptimal solution. So you may find, say, a good solution, but it could be not optimal. Again, the example from chess. You have two alternatives. For example, you can take a knight of opponent, and probably you can like met your opponent. So, but if you never do this action, you never choose this action. But you know that to have the opponent's knight is good, so you take this action. And epsilon greedy policy actually it deals with such kind of suboptimality, and it's better actually than the greedy policy, because you with some small probability epsilon, you take random action, and that's why your agent could learn some new things, and if it finds better action, then after a while he will use this better action. And we have other common policies. I will talk probably later, maybe after my presentation. I don't want to spend time for that now. So in our case, we will choose this epsilon greedy strategy or policy. So we will choose our action A. Q is our current estimate of state and action. So the function that takes argument state and action. And with some epsilon, probability epsilon, we will take random actions. So what is this magic estimate function or something like this? So actually, this is the definition of this kind of function. So Vs, this is the current estimate of the state. So it means that how many rewards we can get if we start from this state. The total rewards, I mean. And at each when we take our action and we go from one state to another state, we need to update this function, actually, to update this current estimate of our states. And we need to use this like a scary formula. Yeah? Actually, this formula is not too complex. Actually, this is QSA. This is the old estimate. You see, we have here and here are our reward, and gamma and Vs prime is the estimate of the next state we are coming to. So if we took this element and add it to the first addendum, we will see that this is simply weighted average of old value and new value. That's it. So it's simple. And alpha, it's actually this is not our angle. This is a learning rate factor. Alpha should be from 0 to 1. If it is close to 0, it means that we take into account only old information, so only old knowledge, our knowledge, and do not take into account new information. So our agents stop learning, actually. And if alpha is close to 1, we don't use our experience. So we just take into account new things. So new rewards we get coming from one state to another state. So alpha should be like something in between, so usually. And gamma is just discount. So it helps to deal with these infinite things like if your model can go infinitely and you can collect these rewards infinitely, so your model doesn't converge. So if you introduce this gamma like 0.9, this kind of coefficient, you will have a good convergence. So let's look at the demo. So what I'm going to do, I'm going to run some number of episodes, say 1,000 of episodes during 1 second. with a time step 10 milliseconds. And after I run another extra episode, and will like record this episode and then play it back for you to look what our agent has learned. So this is our cube. So it founds it founds a solution very quickly, just 1,000 of episodes, and it's enough to gain enough knowledge to find a good solution. So let's do its life a little bit harder. So power is like a power of our reaction wheel. So now our motor is not so strong. So you see, yeah, actually it's not bad, but it's not so good as when we see this first time. So let's do its life again a bit harder. So I see that, you see, 1,000 of episodes is not enough. So let's add.
Did you increase your gamma?
No. I just I'm going to add actually number of episodes. Yeah, say 5,000. It's not enough, you see. Oops. Let's do 15. Yeah, no, it's not. You see, it's better, but not good. Let's do 25. And I'd like to draw your attention. You see, our state, final state. 18 is our angle, -5 our angular velocity, and -49 is our angular speed of our reaction wheel. Yes, and if we see our states some integers. So actually I discretize this continuum state. So if you know angle, so if you will work with float with actual measurements, you will have like millions, billions of different. So any new state will be new, and that's why you need to discretize this. So I split this from -p to p to pi. I split into like 60 ranges. So that's why I have like 30. It means close to this. Sorry, not minus pi, but pi is divided by 4 actually. So our angle. Yeah, and now we see that it found the optimal solution. See this? Here is a summary of my previous experiments. So some of them I just showed you. So we see that, like, for this kind of power we need more episodes. Now I'd like to show you another example from other space, from other area. I'd like to show you a board game Gamoku, so, or 5 in a row, and show you that actually we can build a software agent that will learn how to play and improve its skills and play and win actually. So the tough thing is this kind of games deals with like a huge amount of states. You see, for Gamoku the amount of states is like a 10 to the power of 100. So it's impossible to do this. So what should we do actually? Yeah. Your thoughts?
We can build 2 reinforcement learning machines and make them play with each other. In a few months, we will probably have a
actually, yeah, good idea. But you know, the problem is that we have lots of states. So you know, we need like an infinite number of time to learn actually all these states.
So we can restrict some range where it would find, but it would look into the future for possible rewards. So every move should be calculated for say 200 steps, 200 variants, and so on.
Maybe. Yes.
So we should limit the deepness of the
Depth. Yeah. Actually, we will use the sparse trees. So we won't use all states we can get. So.
At least every move should cut off a lot of thousands of variants, options.
Mm-hmm.
The first one is limited. We shouldn't find for the all possible from the first move. We shall look, and every move should cut off thousands of.
Yeah. So we shall select only good moves. Actually, it's another thing how to do this. But let's assume that we can do this. So we have some heuristic how to like separate good moves from all other moves. So we have this sparse tree. So at each state we have from 5 to 10, maybe more, little bit, good moves actually. And we will build our software agent on this sparse tree. So this is an example actually. So this is our position, and our heuristic selected 3. You see 3 good moves. 1, this and this. So our 4 elements of reinforcement learning: state. This is simply board position, the board position. Actions, enforced moves. So when you see that your opponent 4 in a row, and you need to do something with this. So you have some kind of enforced moves. And if you have no enforced moves, you find these good moves. So policy is epsilon greedy policy, the same. And the rewards, we have only one delayed reward. When we win, we got plus 100. When we lose, we got minus 100. So let's see how it plays. So I have actually two kind of agents. One agent is a simple agent or random agent. He will play for blacks, and our intelligent agent will play for whites. Blacks has an advantage of the first ply. So and it was proved that this is enough to win, actually. So our problem is quite tough.
We don't have time for questions.
Yeah. Okay. So I'm finishing. So you see, it has one enforced move, so it does this. It takes this move, and sometimes it has some good moves, like six good moves. And the simple agent just choose randomly from these 6 good moves. But our agent, intelligent agent, he plays these episodes, and he simulates the party to some depth, and select the moves intelligently. So whites won, and you see. Okay, so I will finish my presentation quickly. So I did an experiment, and you see whites lose at the beginning, and after five or 7 parties, they learned something like 20,000 of states, and starts to win, like 50-50. And after 15 parties, our intelligent agent always win. So it looks like you have two pools of terminal states when whites win or when blacks win. And the whole party is like a graph between these two terminal states. So about a few words about applications. So system control, we saw the example with this cube. Playing games, simulation, animal learning. A few words about reinforcement learning. So reinforcement learning deals with trial and error approach, and it works very good with delayed rewards. So here is my contacts. Thank you for your attention, and sorry for like this short. I had to like be quick at the end.